At the microscopic level, magnetism is generated by the spin and angular momentum of individual electrons. But micromagnetics takes a step back. Instead of tracking billions of discrete atoms, we average their behavior to define a smooth, continuous vector field. As we see in this 3D grid, the magnetization field, M, represents the magnetic dipole moment per unit volume at any given position in time. Inside a ferromagnet, there is a rigid constraint. The magnitude of this magnetization vector is pinned to a fixed length, known as the saturation magnetization. This means the continuous field can only evolve through rotation. The arrows can change their orientation, but they cannot change their physical length. Quantum mechanics dictates an exchange interaction that strongly prefers neighboring electron spins to align perfectly parallel to one another. If that interaction is driving the system, we might expect every ferromagnet to consist of a single uniform field pointing in one exact direction. But in reality, that very rarely happens. This equation shows the total magnetic free energy functional. The structure of a magnet is determined by 5 competing penalties. Exchange energy wants alignment. Magnetostatic energy wants to minimize stray external fields. Anisotropy prefers specific crystal directions. The Zeeman term aligns the field with external forces, and the magnetoelastic term couples the magnetic state to physical strain. The magnetization pattern we observe in a physical material is simply the configuration that mathematically minimizes this total energy. By calculating the precise balance between these 5 terms, we can predict exactly how a physical ferromagnet will behave, from the formation of static domains to high-speed precessional switching. The first term driving the system is exchange energy. Arising from the Pauli exclusion principle and Coulomb repulsion, it acts as a strict penalty against spatial variation. It demands local smoothness. Looking at the integral for exchange energy, the cost is calculated using the square of the spatial gradient. This mathematical form means the system measures the local curvature of the vector field and aggressively punishes sharp bends or rapid changes in direction. If exchange energy acted alone, the material would be perfectly uniform. But as we see here, a uniformly magnetized block pushes magnetic flux lines out into the surrounding space. Creating this large stray field requires a massive amount of magnestostatic or demagnetizing energy. According to the magnestostatic Maxwell equations shown here, any time the magnetization has a component normal to a surface, it acts as an effective magnetic pole. These poles generate a demagnetizing field that directly opposes the internal magnetization, incurring a severe energy cost. To lower this cost, the material fractures. The block splits into adjacent regions pointing in opposite directions. This anti-parallel arrangement collapses the external stray field, neutralizing the magnetostatic energy penalty. The system willingly pays a local exchange penalty, where the regions meet, to achieve a massive global reduction in stray field energy. These regions are magnetic domains. They are the direct physical manifestation of the system solving a mathematical optimization problem, balancing the demand for local smoothness against the cost of global field leakage. The boundary where these 2 domains meet is called the domain wall. Because the exchange energy relies on the gradient squared, an instantaneous 180-degree flip between adjacent atoms would cause the exchange penalty to spike to infinity. Instead, the rotation must happen gradually across a finite width. This introduces the third mathematical term, magnetocrystalline anisotropy. Spin-orbit coupling ties the preferred direction of the electrons to the physical symmetry of the crystal lattice. As shown in this density function, the energy is lowest when the magnetization aligns with a specific easy axis, and it scales with the sine squared of the deviation angle. Inside the domain wall, the vectors are forced to point away from the easy axis, driving up the anisotropy energy. Here, the 2 penalties compete directly. Anisotropy prefers the wall to be as narrow as possible to keep the majority of the material aligned with the easy axis. Exchange prefers the wall to be completely stretched out to make the rotation as gradual as possible. The exact width of the domain wall is determined by solving for the minimum of both terms. As derived here, the physical scale of the wall is proportional to the square root of the exchange stiffness divided by the anisotropy constant. The final 2 terms in the functional are Zeeman energy, which forces the field to align with externally applied magnetic fields, and magnetoelastic energy, which calculates the interplay between magnetic orientation and physical strain on the crystal lattice. A static magnetic domain structure is not a fixed physical object. It is a frozen equilibrium, the exact geometric configuration where any further adjustment would increase at least one of these 5 mathematical penalties. To predict how a disrupted magnetization field moves, we take the variational derivative of the total free energy functional. This calculates the effective magnetic field, a single vector representing the combined gradient of all 5 energy terms pushing on the material. A common misunderstanding is that the magnetization simply slides straight downhill in the direction of the effective field, like a ball rolling into a valley. Because magnetism is tied to angular momentum, the response to a force is torque. The Landau-Lifshitz equation describes this motion. The cross product of the magnetization and the effective field dictates that the time derivative is perpendicular to both vectors. The magnetization does not move toward the effective field, it precesses around it, much like a gyroscope. This mathematical structure strictly enforces the physical constraint of ferromagnetism. Because the dot product of a vector with its own cross product is 0, the magnitude of the magnetization vector remains perfectly constant throughout the motion. Pure precession conserves the total energy of the system. The vector will orbit the effective field axis indefinitely, never actually reaching the energy minimum. In a physical ferromagnet, the precessing spins eventually bleed energy into the surrounding environment, exciting microscopic lattice vibrations and emitting invisible spin waves. This allows the system to finally lose energy and relax. To model this, the Landau-Lifshitz-Gilbert equation introduces a second component featuring the alpha parameter. This dissipative term generates a secondary torque that pushes the magnetization vector directly toward alignment with the effective field. The resulting dynamic is a spiral trajectory. The magnetization precesses rapidly, but continuously collapses its orbit until it aligns with the effective field, and the torque equals 0. This sequence of mathematical logic scales up to dictate the macroscopic behavior of our infrastructure. The dynamics of the LLG equation determine the energy loss to hysteresis in the core of an industrial motor, the minimum switching current required for spintronic computer logic, and the stability of data stored on a hard drive. By treating the material as a continuous field, defining the precise costs of the 5 energy penalties, and applying the LLG equation, Micromagnetics successfully reduces the incredibly complex quantum behavior of trillions of individual atoms into a highly predictable mechanical macro system.